Greetings, Ballston Spa AP Physics students. Before we get started with Simple Harmonic Motion, which is our next physics unit, we need to do a little math work first. I believe you haven't learned about derivatives yet in pre-calc class, so we need to talk a little bit about what a derivative is and how it can help us from a physics perspective. So from our perspective, as the slide says, a derivative is a calc tool that will help you find the slope of a line, or better yet, of a function. If you think about it, we find slopes all the time in physics class, but we have not needed the derivative tool because we've only dealt with constant slope lines up till now. That's important. All the lines that we've used in algebra-based physics have been constant slope lines or straight lines. It does get more complicated when you start dealing with an actual curve, like the dt graph shown below. So let's say we have a parabola whose equation is y equals 3x squared. So this guy here, y equals 3x squared. I can't really ask what the slope of the parabola is if I want to find the velocity, because obviously there's an infinite number of slopes on a parabola. For low time values, the tangent line starts out low and then gets a little steeper and a little steeper. So if you draw tangent lines to the curve, if you find the slopes of those tangent lines, it would help you evaluate what the velocity is at that particular point in time. But that would be just kind of an approximation, because we wouldn't be 100% certain when we draw a tangent line if we got it right. So even if we find the slope of the tangent line, we're never 100% certain. So what we want to do then is to use this very cool tool of a derivative. And the derivative is essentially a function that is the slope of the original curve. The way you take a derivative, if you have something of the form y equals ax raised up to the b power, ax raised up to the b power, the derivative would be take the b, bring it down in front, and multiply by the a coefficient, and then keep your x, and then take your b power, your exponent, and drop it by 1. So in the above example, we had the curve y equals 3x squared, so the derivative would be take the 2, bring it down in front, and multiply by the 3. That gives us the 6. And then the x squared, the exponent is 2, drop it by 1, and that gets you 3x to the first power, or just, 6x to the first power, or just 6x. So we would say the derivative of 3x squared is 6x. Now, what does that do for us? It's actually quite amazing. If you wanted to know, in this previous example, where is the object at 3 seconds and how fast is it moving, to answer the question, where is it, you would go to the original position, or the d function. We could have called this d just as easily as y, which is 3x squared, so you could plug in 3 seconds there. So 3 squared is 9 times 3 is 27. You can see the particle would be at 27 units, or hopefully meters. And then if you plug the same 3 seconds into the derivative equation, where x is really time, as in most of our physics graphs, you would put in 3 seconds here. 6 times 3 is 18, so the speed of the particle would be 18 meters per second. That really is amazing if you think about it, that we can do that. So hopefully this lends a little bit of clarity as to why our 3 graphs that we met earlier this year when we were doing kinematics, for uniform acceleration, we had a dt graph that was curved like a parabola. Then we had a vt that was a constant slope, non-zero line. And then we had an acceleration graph, an at graph, that was a slope of 0. So if you think about it, if the original function was 3x squared, check, that's what that looks like. Then you take the derivative, and notice it's a straight line now because the x squared has gone down the x to the first, so check, that makes sense. And then if we take the derivative of 6x, that would give us the acceleration, because the derivative of velocity is acceleration. So let's use our rule when we want to find the derivative of 6x to the first power. Bring the 1 down, multiply by the 6, keep the x, and drop the exponent by 1, so that's x to the 0. And notice our fun little fact here in the corner, x to the 0 is 1. So that means the acceleration would be a constant. It would be 6 meters per second. And notice that we have a constant line here. Check, that makes sense. I know this says 1, but I didn't make my numbers here to match the graph. But in our case, this would be a 6 right here. So hopefully the graphs for uniform acceleration now make sense. Okay, the good news is now you understand a little bit about derivatives. It's simply a function to help you find slope. The bad news is we're not going to work with dt, vt, and at graphs, so to speak, in simple harmonic motion, at least not parabolas and linear versions. We're going to work with sine and cosine functions. So now that we understand a little bit about a derivative, it's helpful to talk about what is the derivative of the sine function and what is the derivative of the cosine function. And we can easily think that through. If we look at our sine curve, this is one period of a sine curve. We're going to look at a few spots. 1, 2, 3, 4, 5. Those spots right there. We're going to estimate what the slope is, and we're going to plot that slope over on the right. So this is our sine curve, and this is going to be our derivative over here, and we'll try to figure out what that curve is when we finish it. So first, let's try to find at 0 here. Let's try to estimate what the slope of the tangent line would be. Now that slope looks about 1 to me, a rise and a run of the same value. So I'm going to plot 1 here. Then if we get up to 90 degrees and we draw a tangent line there, the slope has become 0. So over here, I would plot it at 0. And then if we draw a tangent line over here at 180 degrees, that looks to be a slope of about -1. Then, if we draw a tangent line over here, that's clearly 0. So we'd be back over here at 0. And then when we draw a tangent line at 360 degrees, notice we're back to having a slope like we did at the beginning. We have a slope of roughly 1. So we're going to want to plot another point at 1. So what have we gotten? Well, if we draw it in, that should look very familiar to you. I know my penmanship with the mouse is not good, but notice we've taken the derivative of sine and it has clearly given us cosine. So as they say in math class, the derivative of sine theta is cosine theta. Now we're typically going to have a t there, so we're going to say that the derivative of sine t is going to be cosine t. All right, let's talk about cosine. Let's take the slope at a few points and see if that can help us determine what the derivative of the cosine function would be. So let's first start with the slope here where the cosine curve is flat and we get a 0. So I'm going to plot that here. And I know what you're thinking. Oh, I bet you we're going to get a sine. Well, we'll see. Now, if we draw a tangent line here at 90 degrees, notice the slope looks about 1, but it's a -1, not a +1. So I'm going to have to put a point down at -1. And then the slope, if we draw a tangent line here, has become 0. So I can plot that. And then the slope here, if we draw a tangent line, becomes 1. So I'll draw it at 1. And then over here at 360 degrees, if I draw a slope, a tangent line, it's back at 0. So I'm going to put a point there. So if we trace that out, it looks a lot like sine, but notice it went down first instead of up. So we don't just have sine, we have negative sine. So we'll say that the derivative of cosine theta is going to be negative sine. In our case, when we're using t's, where time is on the x-axis, we'll have the cosine of t is negative sine of t. So to summarize in simple harmonic motion, we're going to have time on the x-axis instead of theta, and there'll typically be a number in front of the t. It's going to be r omega. Again, you remember your old friend. It's not w, it's omega. And we have our t here. So the little extra trick here that you should know is that when you take the derivative of sine omega t, the omega pops out in front, and it does go from sine to cosine. Hopefully you were expecting that, and you get your plain old argument back. So for our simple harmonic motion unit, when we take the sine of omega t, it's going to be omega cosine omega t. And in a like manner, when we take the derivative of cosine omega t, again, the omega pops out every time you do it. Whatever's in front of the t pops out front. That's part of the rule. And the negative still shows up. When you take the derivative of cosine, you get negative sine. So the derivative of cosine omega t is going to be negative omega sine omega t. So for example, if we had a position function of 4 sine 2t, when we take the derivative of that, of course, sine always flips to cosine. And whatever's in here pops out front and gets multiplied. So 4 times 2 will be 8. And then you always keep the argument at the end. The argument always comes back here, the 2t. So the derivative of y equals 4 sine 2t will be 8 cosine 2t. I hope all that makes a little bit of sense. It certainly will as we start using it more. We'll be using it every single day in our 3-day unit of simple harmonic motion. So hope you enjoyed, and we'll see you at the start of the simple harmonic motion unit.